I wanted to give you a numerical example for this graphical analysis associated, the graphical analysis of the ex post moral hazard issue. Let's suppose that the demand for physician services is given by the relationship P equals 1,000 minus Q. So at prices above 1,000, nobody would ever go to the doctors. And then as price dropped below 1,000, every dollar drop in price would lead to one more office visit demanded. Let's say that the marginal cost of providing a visit is $500 between the nurse's time, the doctor's time, etc. Let's just say it's just constant. That's a simplification. But let's say that the copay is $100 a visit. And what I'm going to ask here is for the following information. What's Q star? That's the what's the economically efficient number of office visits. I'm going to ask for Q prime. What's the actual number of office visits under the copay? And then I'm going to ask for what is deadweight loss. All right, well, let's get started. This is very typical of the kind of problem that I would ask students on the basis of the material to test mastery of material in Chapter 11. All right, well, let's start this off by drawing the right framework. And the right framework consists of a two-dimensional graphical axis, axes, I guess, is the plural. We have an x-axis and a y-axis. The price is always on the vertical. And his price is in dollars per visit. Pardon my poor handwriting with this sort of sticky stylus. And then the quantity will be visits per, I can't remember what I said last screencast. I think this is a weekly demand function. And then to graph this, notice that I've got this relationship P equals 1,000 minus Q. Let's just graph the endpoints. We can see it's a straight line. We know this because it's in the form of y equals mx plus b. That's here m is -1, the slope is -1. B is the y-intercept, it's 1,000. All right, so if Q were 0, P would be 1,000. That's how we get our y-intercept. And then this is a fairly simple function. Notice that if P were equal, I'd have 0. If P were equal to 0, I'd have 0 equals 1,000 minus Q. I could add Q to both sides. Q is 1,000. So this demand curve is a little more elastic than what we see in the real world, but it's got the virtue of being fairly easy to work with. X and Y intercepts are both equal to 1,000. All right, well, marginal cost is equal to 500. That's the midpoint. Pretty easy to find. Halfway up the y-axis, halfway across the x, the range of x from 0 to 1,000. You can solve that algebraically too. But Q star, remember that this was our socially best outcome. So Q star was equal to 500. I'm going to change my color and ask what's going to happen when we, instead of paying the full marginal cost of the visit, we pay just 100. Go to blue here. Well, if the copay were just 100, well, then people are going to go to the doctors as long as the value received from a single doctor's visit is greater than 100. And that's going to bring us to this outcome here. What quantity is that? Well, we can just plug 100 into this. 100 equals 1,000 minus Q. Let me do the algebra. 100 equals 1,000 minus Q. I can subtract 100 and add Q to both sides, and then positive Q, negative Q, those cancel over here. Positive 100, negative 100, those cancel over here. And I'm left with Q equals 900. So Q prime, that's what we're talking about right here. Q prime is equal to 900. And then deadweight loss is a little bit harder, but not that much harder. Remember that every visit costs us 500 to provide, and the value of each visit is given by the demand curve. If I want to know the social loss associated with that, the moral hazard associated with that insurance, I'm looking at this area shaded in blue. Notice that's a triangle, and I just have to remember from my high school math, which may have been quite a while ago for many of us. Remember that the area of a triangle is 1/2 times base times height. Notice that I've got a base of 900 minus 500, that's 400, and I've got a height of 500 minus 100, that's also 400. So 1/2 times 400 times 400, that equals 16, 4 zeros, 160,000 divided by 2 equals $80,000 per week in social costs. And that's a numerical estimate of the waste associated with this ex post moral hazard. Now later in the chapter, just to flag a very important discussion at the end of this chapter, moral hazard can be positive. There's such a thing as beneficial moral hazard, and there's two sources of the beneficial moral hazard. One is that this phenomenon works for preventive care as well as for treatment of conditions that are already developed. And when we talk about reducing the cost of preventive care, well, then more preventive care is demanded, and we see an increase in health outcomes. And then the other aspect of beneficial moral hazard comes from Nyman, I believe is the author. His or her, I can't remember what the gender of Nyman is, but anyway, a very important study argued that when we are insured, there's actually a very important income effect that in real terms, insurance makes us more wealthy. And that was that discussion. Remember, we talked about what would happen if we eliminated Medicaid. Maybe health outcomes would not change that much because people would find some way or another to address their health condition, but in so doing, they'd be bankrupt. Well, the fact that they don't have to do this anymore, the peace of mind that comes of having insurance against these disasters, makes people better off in real terms. And so if that's the case, then we aren't just looking at a static demand. Demand shifts to the right. The income effect causes us to demand more of things, including health insurance, and that it's not all beneficial moral hazard, but there's a beneficial aspect to the moral hazard issue if there's this income effect. Now, the graphical analysis gets a little complicated. I'm not going to hold you responsible for that, but I just wanted to qualify this notion that moral hazard always leads to this ex post deadweight loss in terms of our usage or overusage of healthcare. That's a big part of the issue, but it's not all of the story.